Okay, this video goes with the 1-4 last page on the student notes. Do you understand and do you know how? So let's look at our essential question. How is inductive reasoning used to recognize mathematical relationships? There's this, it's almost like the scientific method. We look for patterns. Make predictions. And test those predictions. So we're looking for patterns. We're making guesses, educated guesses based on the patterns. And then we're testing the predictions to see if they work. And if it works, then we have a good inductive reasoning. If they don't work, we modify it and we keep trying. Okay, let's look at number 2, error analysis. Esteban made the following drawing and stated his conjecture as: the altitude of a triangle always lies inside or alongside the side of the triangle. Now, an altitude is defined as a line. So an altitude, it's a line that passes through the vertex. Which is, there would be a vertex, this would be a vertex, this would be a vertex. These are all also vertexes, or vertices. So there's actually an altitude to each one. There would be an altitude to this one. There'd be an altitude to this one. There's an altitude to this one. There's an altitude to there. Let's see what we got here. We got an altitude perpendicular that passes through the opposite vertex. Now look at this one though. To have an altitude here, we kind of have to extend this line out. This is the base here, the opposite side line, and this would be the altitude that would go with that vertex. So an altitude is a line through THRU, through the vertex that passes, that is perpendicular to the opposite side. The opposite side. So the ones that he drew work, but if you look at this altitude here to this vertex of this triangle that he drew, the altitude actually passes outside the triangle. That's a counterexample. I found a time when his conjecture did not work, which blows the whole hypothesis and makes it wrong. Let's look at number 3. What type of statement results from deductive reasoning or inductive reasoning? We call it a conjecture. It's untested. Well, it's unprovable. But it seems to work. Or we could call it a hypothesis. So we make a hypothesis. As long as we don't find a counterexample, we assume the hypothesis works. But it's really hard to kind of just prove it. We just can't find a time when it doesn't work. Okay, let's look at the do you know how section. What appears to be the next 3 numbers in the pattern. Okay, so I would maybe look for constant differences here to see what I could get. 4 plus 7 makes 11. 11 plus 7 makes 18. 18 plus 7 makes 25. We can see that the next 3 numbers are all gonna go up by 7. Just continue the pattern. So 25 and 7 is 32. 32 and 7, 39. 39 and 7, 46. And the pattern goes on. So, okay, what conjecture can you make about the number of regions created by n unique diameters? I'm thinking with this one, make a table and then try to find the pattern from the table. And they want us to come up with a rule when they talk about n. They want us to use n like an x and make a rule. So 1 diameter, 2 diameters, 3 diameters, 4. And let's maybe go for 5 and 6. And then we'll try to find out what the rule would be. With 1 diameter, we have 2 regions. 2 diameters, 4 regions. 3 diameters, 6 regions. 4 diameters, 8 regions. So I can kind of see a pattern right here. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. So I'm thinking 5 times 2 is 10. 6 times 2 is 12, and so on. And ultimately, 2 times n is going to be the rule that we have. So 2 times n, 2 times 3, 6. If we had 100, we'd have 200. So 100 diameters would give us 2 times 100, or 200 unique areas. So this one we could kind of see directly from the initial table what the pattern was. Let's look at number 6. Can you find 4 examples that are true or a counterexample? Counterexample means untrue for the following statement. So for every integer n, the value of n squared plus 1 is odd. So let's talk about the integers again. Integers could be negative whole numbers and positive whole numbers. Those are the integers. They keep on going in both directions. So let's look at these. Negative 1 squared. That's going to be 1 plus 1 gives us 2. Right there, found one that doesn't work. Same thing would work for what about 0? Well, it came out. What about positive 1? 1 squared plus 1 gives us 2. Here's another counterexample. All it really takes is 1. Either one of these is enough to shoot the whole thing down. So we can't say that for every integer, n squared plus 1 is odd. Now if we did it for 2, we would get a 5. For 3, we get a 10. Here's another one. 3 squared would be 9. 9 plus 1 would be 10. 3 would be another one we could use as a counterexample. So it doesn't say we need to find 4 counterexamples, but we can pretty easily find at least 3 counterexamples. The negative 3 would be another one. 4 squared plus 1, that's going to work with the rule, but tons of counterexamples as to why it doesn't work.